whether my okay. Then today maximum I will try to complete the theoretical part, okay, as we do in the previous project. 1 day is for theory and 1 day is for design and 1 day is for verification. If we need one more day, we can take, no problem. Okay, if we can't complete in 3 days, no problem at all. We can take one more day and we can complete. We can extend how many days we need, we can take. Okay, and I will try to complete from my side. This is what today's agenda is. Okay, we will start the session, and if anyone come, they can join in the middle. Okay, so let's start. Okay, my screen is visible now. I'm presenting my screen. Is it visible? Hello, my screen is visible now.
Yes, sir.
Okay. Okay, then let's start. See, previously we come across with RISC. Okay, what is meant by RISC? It is reduced instruction set computer. Okay, what it means? It is a ISA. ISA in the sense instruction set architecture. Okay, so in order to do a process, we need a instruction. So that instruction should have some structure. Structure in the sense what that instruction is of, how many bit it should be, and what each bit represent like that. Okay, so what is RISC? Actually, RISC is a reduced instruction set computer and it is open source. Why we need RISC? Because it is open source, free to use, and it is simple and clean instruction format. As we see yesterday we decoded a 32-bit instruction. Then you might know, no, like we see the frame format and how to decode that instruction, 32-bit instruction, and how the result come like that and all we see yesterday, no. So the same. That's why they are telling like it is simple and instruction. Okay, simple and clean instruction format. Okay, then this is the RISC architecture. And if someone asks you to explain means you can explain this. First, there is a instruction memory, and inside that memory we have that inside that instruction memory we have the instructions. Okay, what are all the instructions we are going to perform? Okay, in our case we had two codes. Okay, one is of 16-bit, one is of 32-bit. So this instruction memory will contain what are the instructions we are going to perform. Okay, that will be contained in the instruction memory, and the instruction fetch unit is used to take the instruction. Okay, then we give it to controller, and the instruction will pass to data path as well. And as I told you yesterday, data path will have ALU, register file, and data memory as well. And this control unit will control all the operations, that is all the ALU operations, and where the instruction need to go, and where it is fetched, and where to load, and where to store, like that. And all these controlling operations will be taken over by the control unit. And then we have a data memory. Data memory, why we use? In order to load some data from a memory to register, we should have a data, no? So in order to store some result, we should have a memory. Okay. In order to store some result, we need a memory. Okay. For that, we use data memory. So we can use the data memory to store something or to load something to the register. Not something, it is a data. Okay. We use data memory to load some data or to store data. Okay. Where we load the data, we take that data from the data memory and we load it to the register file. Okay. Okay, this is the difference between RISC and SIS. SIS means complex instruction set computer. Okay, which is the instruction set that architecture will be complex, and it will not have some aligned instruction, fixed instruction size. Okay, and it is difficult to use, but it also has its own advantages. But more than that, risk have the main advantages. Okay, as of our project, we should concentrate in risk as well. Okay, then these are the extensions. What is meant by extension? As of our project, we are using IE extension. Okay, so IE extension in the sense it is integer, and we have some more extension like F is for floating, and D is for double precision. Like that, we have extensions. Okay, and RISC V32I in the RV32I in the sense it is an instruction it is an integer extension, and our instruction is of 32-bit length. And RV64I in the sense it is also an integer extension, and which is our instruction is of 64-bit. Okay, you can decode this now in this name. And yeah, this is the main purpose. Actually, yesterday we saw two codes. One is RISC-32I and one general RISC, which is of 16-bit. Okay. And see here, our RISC-V RV32I have 32 general purpose register and 32-bit fixed length instructions, and we can perform load store architecture as well. Okay. And these are the instruction formats. See, frame format is different. Okay, instruction format is different. Instruction format in the sense what we are going to perform, like R type, I type, S type, B type. In the sense we are going to transfer our data through registers, or we are going to perform the ALU operations by having our data inputs in the registers, or we are going to pass the data immediately, like that and all. We have instruction format. Okay, that is what this R type, I type and all. S type store instruction. Branch type in the sense if we have a data, it is not the exact data which is going to perform in the ALU. Okay, that data is actually address. So if we go and see in that address, there might be some data. Okay, we take the data and we perform the ALU operation. Okay, so these are the some of the instructions. Okay, for R type we have an instruction, and for I type we have a particular instruction, and this is frame formats. Okay, see, this is instruction formats, and for each instruction format we have different frame format, and every frame format is of 32-bit size. Yeah, because why? Because our variant we are taking RV32I. Okay, so our instruction will be of 32-bit length. Okay, so for each instruction formats we have different frame formats. We have different bits will act as a different purpose. Okay, see here, for R type we have different frame formats. For I type we have different frame formats, and for S type we have different frame formats. And yesterday we see no R type and I type, and you can notice that in I type from 20th bit to 31st bit we are passing some value immediately. Okay, yesterday we passed 1 in that value and we get the result as 1. And R type means we are going to perform the ALU operation by loading the data to the register. Okay. And see, for everything there is a different frame formats. Okay, for B type there is a frame format. For U type in the sense upper immediate, we are going to pass some value in the upper bits. See here, 20-bit immediate value. So upper 20 bits will be the values will be passed. Okay, and J type is the and then pipelining concept. What is the pipelining concept? Pipelining is a technique used in CPUs. Why we are using this technique? To overlap the execution of multiple instruction. Okay, and we performed that, and I showed you a diagram, and there are 5 stages: instruction fetch, instruction decode, execute, memory access, and write back stage. Okay, so if we have 2 instructions, if one instruction is in instruction fetch stage, and if that instruction move to the instruction decode stage, our second instruction will come to the instruction fetch stage. Okay, this is what pipelining is. So it will overlap the executions. Okay, so that we can improve the performance of our CPU. And then there are some advantage of fixed length instruction. That is, it is easy to decode. Every instruction is of same size. So we can, our hardware logic will be decreased, and we have better performance and faster instruction fetch and decode reduces the pipeline stall. Okay, pipeline stall in the sense that waiting. Okay, if we need to decode, if we need to fetch, we need to wait some time. No, if we have fixed length instruction, that stalling will be reduced. Okay, or else we need to extend our stall. Okay, then these are some real world application. Where are we using this RISC-V? And as conclusion, as I told, what are the uses of RISC-V, like that. Okay, then passing to the design, as we see yesterday, not yesterday, last 3 days we are seeing RISC-V only. So this ALU control is to control the ALU operation, like function 3. Function 3 of 3 is of 3 bits. So if we have 111 as a bit and we have our ALU operation, these both will be concatenation. Okay, these both will perform a concatenation and form a 5-bit. Okay, so based on the 5-bit, we are going to decide what operation we are going to do. Like that, if we for controlling the ALU, we are going to use this ALU controller. Okay, then next block is controller. Why we are using this controller? It is for controlling the opcode, and it will decide which type, which extension, which frame format it is of. Like that, it will control. That is, which extension format it is. Okay, which format this opcode is for. Like that, it will decide, and it will, based on that opcode, it will turn on some signals and it will turn off some signals. Okay, that is what this controller is of. It is going to control the signals. Okay, for based on our requirements. Okay, then data memory. Data memory, as I told you before, obviously as we get a result, we are going to store the data in some place. Okay, for that we use data memory, or if we need some data for our ALU process. Okay, for that we are going to load some data in the register. For that we are going to use data memory. And we all know there is two logic. It is not only for data memory, particularly this block. See, we can use in anywhere. If we need to store some data in an address, we are going to use this one. Memory address is equal to write data. Or if we are going to load something, we are going to use read data is equal to memory address. Okay, this is generally in all place we are going to use. Wait, more than this, here it will be more clear. See here, for writing the data, we have a memory and we have address, and in that address we are going to write some data, that is register write data. And see here, for reading some data, see here, assign, we are reading data. How we read data is equal to that particular memory location and that memory we are assigning here. Okay, so this is general for everything. Okay, if you need to perform read, if you need to perform write, you can use this format. Okay, okay, then flip flop. Why we need flip flop? Is there any idea? See, flip flop is used to transfer the PC address, PC instruction. PC in the sense program counter. So what program counter hold? Program counter will hold the address of the next instruction which we need to be fetched. Okay, that is what this flip flop. Why we are using flip flop here? Okay, so why we are using D flip flop? Obviously, when we pass a input, our output should be same. Okay, as we pass the instruction, as we pass the address, that address should be same at the output side. Then why we need to use this flip flop? Because of this clock, a synchronization. Okay, a synchronization purpose, for a synchronization purpose. Okay, so why we need synchronization? At a particular clock type, our PC should be moved to the further operation. Our PC, that is, our PC will hold some address, no, address of the next instruction. Okay, so that should be executed in the perfect clock cycle. That is what this flip flop is used of. Okay, and then this is for immediate generation. That is, we are going to generate some immediate values. For that purpose, we are going to use this immediate generator. And then instruction memory, as I told you yesterday. See, here we have instructions. That is, these are the instructions that we are going to perform. Okay, this is the work of the instruction memory. This is the characteristic of instruction memory, to store the instructions. Okay, And we have mux, it is for selecting the data. Okay, as we told yesterday, we can select either if you need to pass the data immediately, you can select, or if you need to pass the data through register, you can select through mux. Okay. And when we need to perform a ALU in modes of register, that is in R type. Okay. R type in the sense register type. That is, wait a second. Okay. R type in the sense register type. That is, we are going to load a value in the register, and based on that value, we are going to perform the ALU operations. Okay. So for that case, we use this reg file. Okay. Then ALU32 will have the exact ALU operations. That is, what are the operations we are going to perform? That will be present in this ALU32. 32 in the sense it is the size of each output. Okay, each output, each instruction, everything is 32 in this. Okay. See here, then data path. Data path will have, as we see in the architecture, data path will have register file, and it have some other blocks also. See, instance memory it have. Instance memory means instruction memory. Okay, instruction memory it have register file, it have immediate generation, ALU32, it have data memory. Okay, as we saw yesterday, it will have the sub blocks, that are the blocks which we need. Okay, to do a operation, we do it in the data path. Actually, based on the instruction, based on our architecture, data path must have ALU. Data path should have ALU register file, and it should have a connection between the data memory. Okay, so we are performing this, and we will connect the ports. Okay, using this instantiations. Okay, then data path will have the additional information regarding this data path, like what we need to assign. See, we are assigned some R type like this, and for particular opcode, what should be our output is like that. See, yesterday we performed, for our function 7, all the 7 bits are 0, and for function 3, all the 3 bits are 1. Then our 4 bit is, that is, our output is 4 bit, which is of 4 zeros. Okay, then we go to this ALU operation, then we search for where this 40 is present, then it is of addition operation. Okay, like that, to connect the ports, we use data path, and some additional information regarding the data path will be given in this data top. And the processor is the main block here, which is going to hold all the major blocks, and from this major blocks, we are going to connect the ports. Okay, see, and we are including this processor in the design. But when it comes to verification, we are instantiating this processor block alone. Okay, we are instantiating this processor alone. Okay, and as I told you yesterday, in the verification part, what we usually do is, wait a second. Okay, in the verification part, what we usually do is, see here, what we did here, there is a output. Okay, and they mentioned like we are going to perform the AND operation. So what it is, in the instruction memory, they have passed a 32-bit instruction, and they are expecting this 32-bit output. Okay, that is all zeros. Okay, see here in the test bench side, the first one. Okay, in the test bench side, the first one, they are expecting all zeros. Okay, for that they are passing this instruction, and if we get that expected result, our point will be 1. Okay, like that, if all our 20 instruction are getting the expected output, we will get 20 points, so that we can identify that, okay, our 20 instructions are correct, it is correct only. Like that, we can identify. It is the process of this test bench. Okay, here we are using like this. If you need some elaborated test bench architecture, you can definitely use that. Okay, or you can create that, no problem. Okay. Okay, then we saw the second design. Okay, yesterday, which is of 16-bit, and same operation what we did in the previous code, the same operation is done here with some alterations with some difference. Okay, we have some difference, but as I told you, we are uh, what we are doing here is we are just following the standard. Okay, that risk-free standard. By following that standard, we can have some difference. Okay, that is what they have did here. Okay, in the ALU path, see, we have all the ALU operations which we are going to perform, like AND, subtraction, add, or like that. Okay, and as I told, in data memory, we are going to store some data, and in register, we are going to load some data, or we are going to store some data to the data memory. Okay, or we are going to load some data from the data memory to the register. Okay, and by loading the data into the register, we will perform the ALU. Okay. Okay, this is parameter where we declare the size, like column, row, like that. Why we are declaring is simply declaring in every place like 16, like that. Simply declaring that bits, we can directly declare the column and row. We can directly declare that word. Okay, it will be easy for us to identify. Okay, and the data path, same. What the previous code contains, same here also. The same duty for data path, not only here. In any risk you go, you check means you have the same architecture. Okay. And here control unit. Okay. And what is the use of control unit? Control unit's characteristic is to control the opcode, not control the opcode. It will check the opcode, and based on the opcode, it will direct our instruction, like what operation we are going to perform, either load word or store word, or we are going to process some data, like that. Based on the opcode, it will turn on some signals and it will turn off some signals, and it will control the total operation. Okay, and these are some test data, and this is ALU control. That is, it is going to control the ALU operations. Okay, for that we use ALU control. And finally, we have some test. Okay, we are going to test this. Okay, for testing purpose, we have some data we stored here. Okay, and we have some parameters stored here, and this is our instruction memory, which is going to store the instruction. And where these instructions are stored, test.probe. So it is a file. So if you go to this file, see there, here our memories, that is instruction memories, are stored here. Okay. And as I told in previous block, mux is used. Why we use mux? To select what we need, which data we need, we can select. Okay. And here we used the SB. Okay, system Verilog test bench architecture. See, we have trans interface. Interface is used for connection between the test bench and DUT. Okay, so in order to make connection between DUT and test bench, DUT means design under test. Okay, so in order to make connection between the design and test bench, we use interface. And inside the class, okay, like generator, driver, and all, we use virtual interface. Okay, why? In the sense, our driver is dynamic in nature, like our class is dynamic in nature. Obviously, our driver is a class. Okay, it is dynamic in nature, and our interface, okay, it is static in nature. So we can't transfer information from a dynamic to static. So what we need to do is we need some dynamic interface. For that purpose, we are using this virtual interface, which is of dynamic in nature. And finally, but at last, we are going to pass our data through the test bench. That is this top module. See here, it is of module, which is static in nature. So it can communicate using the actual physical interface. Okay. Then we have generator to generate the transaction, and we have driver to drive the given transaction to the DUT. Okay, that is to the design. And we have monitor where we receive the output of the design, and we check what are the outputs we received. And then scoreboard, it will check whether the received output, which we received from the data is matching the expected output. Okay, and this is the transaction which we actually pass. Okay. And finally, we have our test bench. Okay. And the environment. In environment, we are going to create all these blocks: generator, driver, monitor, scoreboard, and we are going to connect the ports. Okay. Ports in the sense Obviously, between two components, what we are going to use for communication is mailbox. In the system Verilog test bench architecture, in order to communicate between two components, we use mailbox. When it comes to UVM, we use TLM ports. Okay. See here, we are passing the mailbox and virtual interface in the driver and monitor, because driver and monitor both have connection between the design, as well as in driver it have connection with the design and generator, and for monitor it have connection with the design and the scoreboard. Okay. And finally we have top level test bench module, and there we instantiated, okay, and there we instantiated our actual design, and we are passing the uh, ports. Okay, what are the input and output connections we use? We will pass here. Okay, actual inputs and outputs. Okay, and as I told you, while instantiating, we have two types of instantiation. Okay, that is port connection. Okay, one is port connection through name, and one is port connection through order. Port connection in the terms of order, port connection in terms of names. Okay, by using this, we will connect our ports. Connecting our ports means nothing, just this instantiation. Okay, instantiation of our design. Okay, inside that we have our signals, no, and the signal should be connected, no. So for that connection, I'm telling. Okay. So this is what we saw in the last three class. And as of now, do you have any doubts?
I have a doubt.
No doubts, or you have any doubts?
Like I have one doubt.
Yeah, yeah, yeah. Ask.
I am asking ki like it's 32-bit that this pipe processor like whatever design is there. For that verification code will be not applicable. Like the system Verilog code.
Yeah, it is applicable. Yeah, that's why I told, like, see, you are asking this risk with 32i. For this, we can write the same like here. Okay. See, here we write system Verilog test bench architecture. No, the same we can write for this. But me, I'm not writing this. Not writing this means I have no time, or here it is not there. Okay, but we can write. Yeah, if I have some free time, I will write this. But as of now, we don't have that. Okay, we need to write. Okay, but we can write. Okay, it is not like for this one, for this particular design, there is only test bench which we can use, which we there is particular test bench design that is like this. It is not like that. Okay, we can design like this.
I mean, so
Okay.
we can design for the 16 like 32-bit also. It is possible to write system Verilog code also, not like 16-bit.
Yeah, yeah.
16-bit.
Yeah, it is possible. See, for 16-bit, we write a system Verilog design, okay, test bench architecture, no, based on the system Verilog test bench architecture, we write a design for testing this 16-bit risk, okay. The same can be written, okay. The same can be written in this 32-bit also, okay. No problem in that. But personally, I didn't write that, okay. That's all. But we can write. It is yeah, I have no time, so I didn't write that. But we can write. Okay, I have some other course. Okay, I will refer and I will tell you. But we can write not only for this, for any design. If there is if you need to write, if you need to verify the design based on the system Verilog test bench architecture, you can write. Okay, this is your doubt, or
Yeah, this one. Like already I make that X5 project account in Verilog only. The system Verilog like not applied, so that's it.
okay, okay. Actually, it is yeah, it is not like that. It is I personally I didn't write that. Okay. That's all. But if we need to write, we can write. Okay, it is always possible. Okay, if I have some time, I should write that. Okay, okay then. Any other doubts? Someone asked. No? Yeah, yeah,
I have a doubt.
yeah, yeah.
Can you go to that 32-bit code? Can you
Yeah.
show it? In that the 32-bit, Oh, no, not this one, the first one, the RISC-V 32I.
Which block?
No, I'm
Oh,
asking the
okay, okay.
first code. That,
Okay, okay,
yeah.
okay. Sorry.
In this, can you go to the flip-flop .sv?
Yeah, here it is.
So you told that this is holding the PC value, right?
Yeah, yeah.
Your PC is PC plus 4 for the
Yeah,
RISC-V. So
yeah.
where are we implementing that?
Yeah, actually, see here. We have instantiated, okay? So we will not increment that PC here inside the flip-flop. Flip-flop's duty is to get that PC and it will give the same PC value. That is the same instruction. Okay, it have the address of the next instruction. So it will take the same instruction address and it will give the output as well. So okay, but PC, okay, wait. For PC, we do incrementation, but it is in different block. Wait, I will show you. Here it is. One second, I'm searching. One second.
Yeah, I think it is in data path. Maybe I saw that in
Yeah, we
data
have the
path.
initialization. That is, we have
Okay,
a
okay.
okay. We initialized this, but yeah, as I told you, see here they have incremented
So
here,
this
right?
line number 50. Okay,
Yeah.
got it.
So we are going to implement here. Okay, flip-flop's duty is to get that PC in and it should give the PC out as it is. Okay, the increment will be done in this data path. And as I told you, no, see here that connections, that port connection. Okay, so here we will connect. So for example, see here for address here in the instruction memory, in the address, okay, inside the instruction memory. Wait, I will show you an example. Okay, see inside the instruction memory there is a address. Okay, we are going to connect this address with the program counter. Okay, why program counter? It have the address of the next instruction which we need to fetch. Okay, so this is what connection is. Okay, this is what port connection is. We are going to connect one module, that is one block, with the another block. So here which block we connected? We are connected this where we have, wait, here where we have PC out, we have PC out in the data path. So we are connecting the data path with the instruction memory. Okay, if we go deep, see here, and finally it is coming out through flip-flop. Okay, and what is the input of flip-flop? That is NPC, in the sense we no need to confuse it. They here itself they mentioned it, it seems. Okay, NPC in the sense that is next PC, I think next PC or PC before it have, I don't know about that, but it is different. It is the next PC. Okay, that is the next program counter which it need to be give. So after coming out, it is the actual program counter. Okay, so this flip-flop's duty is to take that PC in and it should give the PC out. Why? Because as I told, it is for synchronization, but that increment and all done by this data path itself. Okay, that is what that is why we are using this port connection. Okay, so it will take care. We are connecting from one port to another port. No, so each block will do its operations. Okay, so as of your doubt, this program counter, we will set the value of the program counter and it will be incremented and it will, see here, NPC. NPC means next PC. Okay, so the next PC, that incremented PC will be will do its incrementation. Okay, in this data part, and that incremented PC, okay, will pass to this flip flop. Okay, and after a clock cycle, that next PC will become the present PC. Okay, I think you can understand. Okay, so previously that PC is the next PC, but after a clock cycle, it is the present PC. That is, it will hold the next address. Okay, that will come out. Okay, that will be taken by this flip-flop. So this is port connection. So see dot D in the bracket NPC count. That is, see here in the flip-flop, in place of dot D, we are going to connect this NPC count. Okay, that is what they are mentioning. Okay. You are clear or you have any doubts? If you are still not clear, you can ask. I will.
No, I got it.
Okay.
I got it. And in the Mux,
Okay, one second.
mux.sv, so we are basically implementing the data forwarding logic, right?
No. In Mux, what we are doing is, actually, Mux is for selection. Basic Mux operation is for
Select, yeah.
selection. And if we go here, see, there are two operations here. See here, they are selecting either we need register data or we need immediate data. That we will select. And they are using for ALU result. Either we need ALU result out or we need that memory data or we need a memory data. ALU result, okay, if we take ALU result, what we will do? We are going to store in some memory. Or if we need to read a data, what we are going to do? We are going to read the data from the memory. So according to our requirement, what we need to do, that will be selected by this mux. Okay. So if you have some other requirement and if you need the mux, you can take one more line and you can take this mux and you can instantiate and you can use whatever you need. Okay. But the basic mux operation is, as we all know, it is for data selection. But as of our requirement, we are using this. As of our requirement, we are using, okay, based on our needs. Okay.
Okay, got it. Thank you.
Okay. Okay. Any other doubts in REST-V? If you have any doubts, you can ask. Or it is not clear. Also, you can tell me. Okay. Like what you. Okay. Okay. As of now, everything is clear. Or if you have any doubts, you can ask.
Sir,
Yeah.
sir, you are mentioning this is the third class, but for us it is
Yeah.
a first
I
class.
will. Yeah.
Uh,
For you, actually, it is a router. No, 1x3
sir.
router. Yeah.
Sir.
Now only we are going to see that. It is
Oh,
like it is a previous project. We have some other friends, no? So it is their
oh,
project. So now we are going to see this router. Okay. So
okay, sir.
you also need some knowledge about router, no? So for that we are all going to take this. We are all going to involve this. Okay.
Oh, okay, sir. Thank you.
Okay. Now we are going to see router. Okay then. My screen is visible now. I am presenting my PPT. It is visible now for you all.
Yes, yes.
Okay then. See, actually router is a network on chip protocol. Okay, so network on chip in the sense, inside our SoC we have plenty of blocks like for memory, for processor, okay, like that for DSP. For that we have plenty of blocks. Okay, so in that blocks we need to send some data and we need to fetch some data. Okay, see, before that, as I told you, we will cover. Okay, as of now, how much we can cover, we will cover. Okay, then we can do the further theoretical part. We can go with next session, or if it is possible, we can complete it with today's session. Okay, so I will try to complete, and if we can't complete, we can take one more session as well. Okay, as of our plan, theory is one session, and coding design is one session, and verification is one session. But if we can't finish, no problem, we can take one or two or more sessions. Okay, I will take. Okay, and we will complete within this week. Okay, I will try to complete. Okay then. NOC means network on chip. As I told you, inside our SoC there are some different blocks. Okay, like processor, and for memory we have a block, and for DSP like that we have different blocks. And to pass some data, okay, inside that blocks, we need a router in the sense, there should be someone to route in the sense to show that where is the source and where you need to give the data. For that routing purpose we need a router, no? So why we need a router? Yeah, we need a router because to avoid the traffic controls. Okay, traffic controls in sense. Okay, traffic control in the sense. See, if there is a source and if there is a destination. Okay, if there is a router, what it will tell? It will give some particular address and it will tell for this address you need to send some data and your destination is this, like that it will give some informations. Okay, if we don't have information and if we are passing two or more data, what will happen? There will be some congestion. Okay, so there will be some traffic will happen, so our data will be hold. Okay, or it may we may have some loss in our data. Okay, or it may take a huge amount of time. Okay, so to control all those things, we need a router. So that router is present inside a SOC, network on chip. Okay, this is what router, basic router is of. And see here, this is the content of the session. Like we are going to see some introduction. Okay, so yeah, I will tell. See, introduction and IO diagram means input output diagram, and basically TCP/IP model means it is a protocol. We will see. I will tell you. And packet format for router also we have a packet format. Okay, so we have a header and we have data payload. We have parity. Okay, for that also we have some packet formats. We will see. And router architecture. Okay, how router is and what are the building blocks inside that. And router input. In input, what are the signals we have? In output, what are the signals we have? And we will see the waveform. Okay, so how the waveform works, how it will be, and when valid is on, what is our input, what will be our output, like that. Okay, and then we will see some detailed explanation. And as I told you before, we will see the design first. We will see today we will try to complete theory, or we will take one more day and we will try to complete theory, and then last we will see the verification. Okay, this is what our plan is for. Okay, and okay, what is router? See, basically router is a networking design. Okay, it is basically for networking. Networking in the sense we have a source, we have a destination. So how into which address we need to deliver our data. For that networking purpose, we need a router. Okay, router is a networking design transferring from one source to the destination. Okay, for in our case, 1x3 in the sense we have one source, three destinations. Okay, see, this is a sample. This is here we have a source and it is passing to the destinations, computer 1, computer 2. Okay, this is a sample. In our case, we have one source, three destinations. Okay, that is what 1x3 router is for. Okay, and one more thing is we are going to pass all our data in packet format. Okay, we will see what it is. Okay, packet in the sense some are stored, some it will have some header and parity checker, some compressed form. Compressed form in the sense it have data payload header. See here, right? See here, this is what packet format is of. We have data here, we have address, length of the data, and we have parity, like that. Okay, parity is to check the correctness. Okay, we will see one by one. Okay, so what is router inside a NOC? Okay, so obviously network concept inside a NOC we have a router, and what is its use? That is what they are given here. Okay, in network on chip, a router is a critical component that manages how data. In our case, data in the sense packets. Okay, how packets is transferred between different processing elements. Okay, cores means see obviously for in basically in our mobile we have octa-core, quad-core. No, so core in the sense a processor which can do a process which can do one process at a time. Octa-core in the sense it can handle 8 process at a time. Okay, it can do 8 operations at a time. Okay, so this is what core is of. Okay, then we have memory blocks, IP blocks within a system on chip, and To transfer data between them, we need a router. Okay, that is what this we need some device which should route. Okay, where we need to deliver our data, where it is coming from, like that. Okay, so that is the purpose of router. A router in SOC is a small, high-speed digital switching element. Okay, and it is responsible for receiving data from packets. Okay, one part of the chip. Okay, receiving data packets from one part of the chip, and it will give any of the three destinations. Okay, but it will give any one. Okay, it will not give the data to all the three. Okay, and deciding where to send them next using routing algorithms. Yeah, routing algorithms, in the sense we have some structure, no, how it is formed, and we have some design, no, that is what they are telling here. Okay, and forwarding them to the appropriate direction. Okay, then there are some importance of 1x3 routers. Okay, and see, a router is actually a networking device that forwards data packets. Okay, between between a computer or inside a SOC blocks. Okay. We will see there are some signals as well. Okay, I will tell you what are the signals and when it should be high, when it should be low, like that I will tell. Okay, so importance of 1x3 router in a network. Okay, efficient traffic distribution. See, as we discussed, it helps distribute traffic. Okay, it helps distribute traffic from one source to multiple destinations. Okay, so for example, if we have some data and we have some address. Okay, but we don't know how to go, where to go, and what are the current data in that address. We need to know that particular information, no, so based on that we can work. Okay, if we don't have the data, obviously traffic will occur, then we can see some slowness in our performance of the CPU. Okay, so if we have a proper router means, then it will be easy to transfer the data. Okay, so it helps distribute traffic from one source to multiple destinations. Okay, useful in fan out scenarios like sending a request to multiple memory blocks or cores. Okay, and improve scalability in the sense, see, obviously we are going to update. Okay, so helps in modular expansion. That is what they are telling. Expansion in the sense that update. If we update, yeah, we can use router as well. Okay, a router, 1x3 router can be used to branch a network. Okay, making it easier to scale up. Then reduces congestion. Okay, then by splitting the input traffic across multiple outputs, it helps reduce data bottleneck. Bottleneck in the sense what? Some congestion means it can't go. Okay, it will stop, or some friction that it can't move, like that. Okay, so it will reduce by using the router. We don't come across with these problems. Okay, and load balancing can be designed with intelligent routing logic to send packets based on a output port. Okay, availability helping. Okay, see, wait, I will explain you in a diagram. Okay. See, if we have here we have two computers. Okay, and if we are passing some data, and what will this router do? It will route where this data should go. If already if computer one have some data or it is doing some process, this router will indicate like, okay, it have some process, so it should wait. And in between the data for computer 2 comes, the router will route to the computer 2. Okay. But if we don't have the router, what will happen is some data congestion will happen. Here some confusion will happen where to go, and we don't know whether there is a process happening or not. Like that, we come across with lots of problem. Okay. For that, router is used, and that is the load balance. Okay, and used in many core systems. As we saw in SOCs, we use router, no, in the NOC. Okay, NOC code, network on chip. It is, and this is basic network, and this is the router architecture. Okay, basically we have five components. Okay, four components we have. That is, we have 3 FIFO and a register, FSM and synchronizer. Okay, synchronizer will be there, and each block will have its own advantage and its own characteristics. Okay, and we will see one by one. Okay, and this is a basic input diagram. Okay, IO diagram, and now we will draw the diagram.
Can I ask one thing? Sir, you use a modem also before router. So what is that? Why?
Yeah, modem in the sense, obviously, why we use modem for some
To
data.
connect?
Okay,
Yeah.
yeah, network. Okay, so after network, we can't see in our home or some place where we don't have some huge works, so where we have some fewer works, fewer loads. Okay, but when it comes to some, you can go, you can see in our college libraries, in our college labs and all. Okay, there is a modem, but there is a router. Why that router in the sense? Yeah, modem will give the network, but that modem will give some data. Okay, it will search some data from the internet and it will give the data. But where should the data go? Okay, so in our lab, in our computer lab, we have around 20 laptops. Okay, so that 20 laptops, if I search, I have laptop one, and if you have laptop two, if I am searching a data, okay, our network will take that data. Okay, our modem will take the data in the internet, and it will give. But where should that data come? Okay, that will be decided by the router. Okay, as of now, the computer one which is used by me. Okay, so that router should route to the, you go to the computer one, like that it should route. Okay, this is what that modem is for. Okay, modem is basically, basic application of modem is like, it will give a data for us. Okay, from the internet. Okay, understood now, or still any, are you or not clarified like that?
Yeah, got it.
Okay. If you don't understand also, you can ask, I can't understand. You can explain some other way like that also. Okay, I'm ready to explain. Okay, then. See, this is the blocks as I told you, and each block have its own characteristics. Okay, so we are going to pass our, we are, okay. Before that, we will draw the diagram. Okay. See here. This is like a basic pin diagram. Okay. The top level. Let's consider this as it is known as a top level. Okay. See. This is a router top level. Okay. Okay then. See, I'm going to perform. I'm going to show you a basic pin diagram. Okay. See here. We have a clock here. Okay. So this is a, we all know why clock, it is for synchronization, and we have a reset. That is, we all know there is two type of reset: hard reset and soft reset. We will see in the upcoming sessions. And we have a read enable. I will write the name of the signal as well. As of now, I'm just telling. Okay, we have three enable signals. Why three? Because we have three destinations. Okay, and then we have a data in, and then we have a packet valid. Okay, and in the output side we have output data 1, output data 2, and output data 3. Okay, and for that output data we have valid output, or that is either that output is valid or not, like that. Okay, and we have a error and busy signal. As we all know, if we send the information, if we send the data, okay, if the destination receive, but we need a confirmation, no, either it is received or not, it is error or it is busy, it have some other works like that. Okay, so we need a confirmation, and we need a acknowledgement, no, for that we use error. Okay, error and busy signal. Okay, so as I told you, the first signal is clock. Okay, the first signal is clock, And the second signal is reset. And here we have read enable. Okay, read enable in the sense it will come from destination. Okay, see, read enable in the sense it will come from destination. So the destination is enabling the read. Okay, it is telling like, okay, I am ready to read. You can send the data like that. Okay, so read enable is used. Let's now read env. Okay, this is read enable. Okay, and this is for destination 0. Obviously, we have 3 destinations now. Let's consider this as 0th destination, and we can consider the second one as first destination like that. Okay, read enable 1. Okay, see here. Then we have read enable for our destination 2. Okay, env for destination 2. Then here we have data in, that is what the actual data we are going to pass. Okay, so obviously we have only one data now, because we have only one source. That one source will provide only one data. So only one data channel, not only one data. We have only one data in channel. Okay, so for data out we have 3 signals, because we have 3 destinations. Okay, then finally we have packet valid, P50 valid. Okay, packet valid in the sense it will come from source. Actually, before performing this, before routing, our source will tell, okay, the packet I'm sending is a valid one. So you can accept like that, it will send. Okay, their communication, it is their communication. Okay, and all these read signals, okay, all these are from destination. Okay, I will send you this this image. No need to worry. But yeah, but in here we need to know. No, that's why destination. Okay, all these are from destination, and this data in and packet. Okay, it is from source. It is from SOURC. Okay, and see here. Now we are going to see the output signals, that is out signals. Okay, so the data out 1. Why data out 0, 1 like that? Means we have 3 destinations. Okay, data out 0 and data out 1, and then we have data out 2, data out 2. Okay, because we have 3 destinations, we have 3 output data, and because of we have one source. Okay, we have only one data in signal. Okay, so this router will route in the 3 destination where we need to give our data. It will be done by our router. Okay, then we have valid out. Valid out in the sense it will be given as it will be given from the given to the destination. Why is, see, our we will give to the destination like this output is valid, like that we will give. Okay, so for that we have valid out, that is the given output is valid one, like that we will tell to the destination. Okay, valid out 0, valid out 1, and valid out 2. Okay, and then as I told you, we have error signal, because in case it is to source. Okay, so after sending a data to the, after sending a packet. Okay, see, from here onwards we can use data will be considered as packet. Okay, after receiving the packet, okay, in the destination side, after receiving the packet, it will acknowledge whether it is error or whether that destination is not received or not, or whether the destination is not received the expected packet or not. That will be acknowledged by this error signal to the source. Okay. Then we have busy signal. Okay. Why this is? Because if we have a source and that source is sending some packet to a destination, but that destination is busy with some other work, this busy signal will be enabled. Okay. And this side, this first three, okay, this first three signals are going to the destination. Okay. Okay. And the next three signals, these three, these will also going to the destination. Okay. Destination. To destination, not from destination. It is going to destination. And then this last two signals, okay, it will be going to source. Yes. Okay. 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 We made a overall router top level pin diagram. Okay. That is a block level diagram. And once again, I will explain you what is going to happen like that. I will explain you once again, and I will ask you if you have any doubts, you can ask. Okay. See here, we have a clock, we have a reset. Okay. And where we are going to send the data, we are going to send the data using a data in. Okay. This data in signal is used for sending the packet. Okay. Sending the packet from source to destination. Okay. So before sending the packet, we will send a valid signal, whether this packet is valid or not. It will be sent from source. Okay. So first source will send whether this packet is valid or not. Okay. And we will send the data in. Okay. And after sending the data in, our destination, okay, our destination, see here, once again, we can, okay, no problem. From our destination side, it will give a signal which is read enable. Read enable is coming from destination. What it means that read enable will indicate, okay, I'm ready to read the input data, input packet. Okay, this is this read enable is off. Okay, it is from destination side. So when the read enable is when the read enable signal is enabled, that means our destination is ready to read the packet like that. Okay, so we will send the data in to any of the data out. Okay, so we will what we will tell is valid out in the sense from one destination, from one source, we are going to send our data out to any of one destination at a time. Okay. So that data, that is the data which come out, okay, that packet which came out to go into the destination. Okay. For that, this data out signal is used, but either that data out is valid or not. Okay. It will be sent to the destination by this valid out signal. Okay. So after sending the packets, okay, after sending the packets, either that packet is correct or not, or whether our destination received the expected packet or not, or it is not received. Like this case happens, it will show, it will throw, or it will give a error signal. Okay. For that purpose, we use this error. Okay. Busy in the sense from a source, if you are sending some packet to a destination, in that case, if our destination is having some other works, okay, it can't take that data. That time it will throw a busy signal. Okay. So this is what the top layer, okay, top level diagram is. Okay. Is there any doubt for you till now? I don't know, like where the signal, why we are using like this. Is there any doubt as of now?
Like here, read enable, why it is coming from destination? Like
Yeah,
also,
actually, Yeah. Continue, please.
Like, according to my understanding, it also coming from the source only. I don't know properly.
Okay, actually it is coming from destination only. Okay, in this diagram, I just for your reference, I put like this, but it should come like this. Okay, it is all correct.
Okay, it is from router to it is coming read element. Acha, acha. Now understand.
Okay, it is like it is not from obviously router is in between. Okay, it is going to route, but before before routing, okay, we have some input. No, that is source. Okay, somewhere our packets will come. Okay, that is what source is. Okay, inside the router, it will convert as packet, no problem, but data will come from anywhere. Okay, that is source, and it will move to some destination, that is some component or any device. Okay, that is our destination. Okay, so here once we are sending the data, but here we need to note one thing. Okay, router is going to route the packets. Okay, packet or data. See, do you no need to confuse like what he's telling. Sometimes he's telling like data, sometimes he's telling like packet. No need to confuse like that. See, in our case, data is equal to packet. Okay, in this project. Okay, why in the sense here we are going to pass the data in form of packets only. Okay, so in case if I am using the word data, you no need to confuse like what he's telling, like he's telling data on time, he's telling packet on time. You no need to confuse because both are same. In our case, we will consider packet only. Okay, so I will also try to tell packet. Okay, in some case, if I unfortunately unexpectedly I tell data, you no need to confuse. Okay, so let us come to the point. We have one destination. Okay, we have one source. Okay, where it is like a input. Okay, it is like a producer. Okay, so from that source we are going to produce some data and we are going to give it into a router. Okay, so router's work is to just route to where to go, to which destination that data in should go, like that it is the work of the router. Okay, so for that we know it like for output we are having different router, for input we are having like a different router. It is not like that. We have a common router, so that router's job is to take the data in and it should deliver the data to the correct destination. Okay, this is what the job of a router. Okay, so in our case we are getting a data, that is data in from the source, and we need to give that source. Okay, we need to give that data in, that is our packet, to the destination. Okay, so before like before giving that packet to a destination, we should know whether that destination is ready, whether that destination is available or not. Like that, we need some acknowledgement. No, so for that we are using this read enable. Okay, so from destination it will give a signal, that is read enable signal. So we can identify like if the read enable is high. For example, in our case, let's consider we are going to pass some packet. Okay, to the destination 0. Okay, to the destination 0 we are going to pass a data. Okay, a packet. Okay, so we are going to pass a packet to a destination 0, but how we know whether that destination 0 is available or not, or it is in busy, or it is ready to accept that packet. Okay, so for that, the destination will give a read enable signal, that is the destination will give a read enable signal to source, which is telling like that destination is ready to accept the data. Okay, so that is what this read enable signal is. Okay, that is why I mentioned here it is coming from destination, because destination will produce, it will tell whether it can able to take that packet right now. Either it is okay with that packet, it have time, it is free to take that packet or not. Okay, that will be conveyed, that acknowledgement will be given to the source from the destination using this read enable signal. Okay, that is why I mentioned here as from destination. This is your doubt or it is something different?
Yes, clear. Actually, directs are not given, so I confused.
Oh,
No.
okay. Actually, it is my mistake only. Okay, no problem. But I will give that. See, this data outs will be go to destination. Okay. And this will come to source. Okay. And this is also a source. This is also going to source. And these two also a source. Okay. Okay then. So as of now, you all clear with this, no? I will save and I will send you. Okay, no problem. I will send you this. You can use it for your reference. And if you have any doubt in this, you can ask. And as of now, you all clear? Or if you have any doubts, you can ask. As of now, what we discussed. Anything like you don't have some better idea on router, what is NOC, or still now what we are discussed with. Okay, in that if you have any doubts, you can ask. Is there any doubts? Or if no doubts, you can tell like no doubts so that we can proceed now to the next. Everyone clear up?
Yes.
Clear, no problem, no? Everything is clear, no? Okay then. There is Rakesh and one more is Charan. Charan is not clear. Huh? Okay, Rakesh, are you clear with this?
Yes, sir.
You are clear, no? Where is Tarun?
Sir, I will. I don't. I
Okay, no problem, no problem. Anyway, I will share the recording sessions as well. So you can go through that, okay? No problem. For everyone, for every day we are sharing the recording sessions, okay? Okay then. Okay, we will move to the next part. That is our architecture. For router also we have code. It is a big code. Okay. So for router, for verification of router, I think we will use UVM architecture. Okay. For that alone, I think it will take 2 days. It will roughly take 2 days, around 2 hour session, I think, because it is of UVM. Okay. So UVM in the sense, obviously, it has, I think it each have three sequencer like that. Okay. I will teach you. Okay. But it will take some time. It is actually a big verification code. Okay. For this, we have that code and I will share. Okay, this is router architecture. As we discussed, register. We all know, no, register's purpose is for storing and synchronization. All this routing signals, all this routing purpose should be in a synchronized way. That is, it should be in a proper proper way. Okay, it should depend on one. Okay, if one operation done, then the next operation need to done. If uh, P40, if we need to pass packet to P40, it should be passed in a synchronized way. Okay, synchronized way means in a ordered way. Okay, in a periodic way. We can tell like that also. Okay, and FSM is like we have some states. Okay, see in we will check. Wait, see here. Where it is? Wait. See for router we have FSM. Okay, FSM in the sense it will tell in next state. Okay, if we are in a state, so what should be our next state and what is our previous state. Okay, so it will tell. Okay, if we have if we are in address decode address state, then what should be our next state should be. Okay, this will be uh, enhanced in our FSM. This should be informed in our FSM. Okay, so FSM is finite state machine and it will obviously tell like if we are in a particular state and what is the next state. Okay, if we are in data load state and if our for example, I'm telling if we are in data load state and if our uh, if our FIFO is full, then obviously it needs to move to the FIFO full state. Okay, or it will need to move if FIFO full is not still it have some space, it need to move to the load parity, that is the final state. Okay, then after loading the parity it should move to the check parity error. It will check whether the received packet is correct or it have some error like that. Okay, so this is what FSM's job is. It is FSM's characteristic. Okay, it is FSM's character. And as I told you, synchronizer will is synchronizers that block, no, it will perform like whether the data, all the routing process, the packets are performing in a periodic way. Okay, in a timely manner, in a proper way. Okay, that is the use of this synchronizer. Okay, and we have register which is for storing purpose and for loading like that. Okay, and finally we have FIFO. Why 3 FIFO? Because we have 3 destinations. Okay, so for 3 destinations we have 3 FIFOs. Okay, and why we are using FIFO? Yeah, who have any idea? Same, we saw in that risk we know. So FIFO will give the exact what we are giving in the input will be given as output. Okay, but if we have some 4 bit of data. Okay, if we have 4-bit data, our FIFO will have 4 flip-flops. Okay, so that 4 bits will be transmitted. It will be transferred serially. Okay, next to next like that. Okay, so why 3 FIFO? We have 3 destinations. Okay, so for routing that we have three FIFOs. Okay, so obviously FIFO characteristic, no, first in, first out. Okay, we get the data in. So whatever the bit we get first, it will come out as first. Okay, for example, if our data have 10 bit, okay, if our input data have 10 bit, so if we need to pass that input data, let's in our way, it is packet. Okay, if our packet is of 8 bit, okay, it is of byte. If our packet have 8 byte, if our packet have byte, okay, let's consider like this. If our packet have 8 byte and it need to be passed to that FIFO 0, okay, then our FIFO will have that particular space. Okay, it will get the first data and it will give the first data out. Okay, it will get the first bit in and it will give the first bit out. Okay, that is what the process of FIFO, first in, first out. Okay, so all this we have particular characteristics. As I told you before, every block have its own characteristic. That is what we saw here. And what are the information on next thing? Wait a minute. Yeah, here. This is the pin diagram. See, right now we saw no a diagram. I draw no in that paint. Okay, that is what this here is. Okay, same. And see here, you can notice this diagram also. Okay, see here, there is that signals are here properly. Okay, that either it is coming to the source or it is going to the destination or it is coming from the destination or not. Like that, we have this pin diagram. Okay, this is you can refer this one also. Okay, and we have the signals like packet valid, reset, data in, read, enable, as we saw in that diagram, in that pin diagram. Okay, TCP/IP model. Why we need this is obviously this routing process. Okay, this routing process is done in a network layer. Okay, so it is important. This routing process is done inside a network layer. Okay, so for that, for your understanding, we are providing this TCP. Okay, and OSI layer. Okay, so for your understanding, there are 7 in OSI layer. We have 7 layers. No, like physical application, presentation, session layer, transport network, data link layer, physical layer, like that. And in TCP also we have 4 layers: application layer, transport layer, internet layer, network layer. Why we are providing this is we need to know in which layer our routing process happening. So obviously it is happening in a networking layer. Okay, that's why in starting itself I told like router is a networking design. Okay, it is used to send packets from the source to destination in the networking layer. Okay, and this is our frame format. Okay, frame format in the sense, wait a second. See, here we have channel. Channel in the sense we no need to confuse. The first 2 bit is of address. Okay, why we have 2 bits? What is the logic of 2 bit? 000110 00011011. Okay, we have 3 destinations. Okay, so 2 bits is enough. Okay, 2 bits are enough to mention that 3 destinations. Okay, so length in the sense this payload length. Okay, see, one data length is of a byte. Okay, 1 byte. Okay, 1 byte in the sense 8 bit. Okay, each data is of 8 bit, and we can have a number of datas. Okay, that will be mentioned in this length. Okay, it is of 6 bit. Okay, based on this 6 bit, we will mention how many payloads we have, what is the length of the payload. Okay, like that we mention. Okay, so each data is of a byte, 1 byte. Okay, so finally we have parity, which is of 1 byte, and parity is used for uh, error checking. Okay, with either the received packets, this whole structure, no, this address, this channel, this address, this length, it is of 8 byte, and this payload, see, basically the first bit, no, first byte, that is this length plus channel, that is this length plus address, it is called as header. Okay, so this header plus payload plus parity, all these together called as a packet. Okay, this is the packet format. Okay, so this parity is used for error checking. Error checking in the sense either the received payload is correct or not, expected or not, or it is that destination received the payload properly or not. Okay, it will check in this parity. Okay.
Sir, I have
Yeah.
a doubt. Sir,
Yeah.
here in packet format you have written a data, so it is from source or destination side.
Yeah,
Like,
actually, our data will be passed from source to destination. Okay.
so these data's address
Yeah.
are from destination.
Yeah. From source. Source. Obviously, we are going to pass our data from source to destination. No.
Yeah, sir. Source but in source side you have given only one data, na?
But see, as I told, okay, before itself I told, no, in our case, we should consider it as a packet. As if I told, unfortunately, I told data, you should not consider it as data. When it comes to router, we consider it as a packet. Okay. So here, not you should not consider it as like a single data. Okay. We should consider this as a packet. Okay. We are going to pass a packet from source to destination. Okay. So for our rough use, for rough purpose, for a rough explanation, I'm using like data. See here they are passing some data, no? Actually it is a packet only. Okay, that is why they are giving here packet valid. Okay, so from source side we are going to pass this packet only. So this first 2 byte, no, the this first byte, okay, it have around 8 bits, no. In that the first 2 bit, okay, it tell us the address. Okay, for example, if this have 00 means, if it has 00 means, this whole packet need to be delivered to the 0th destination, like that. And this data, see, each data location will have 1 byte. Okay, so how we can customize based on this length. Okay, how many data we have, we can given in this length itself. Okay, so this length plus channel in the sense address. Okay, this length plus address wholly considered as header. Okay, so the first byte is header, then we have data payload, then we have parity. This whole thing is considered as packet, and this packet is sent from source to destination. Okay, you no need to confuse like, oh, he told like data. Oh, then the data will be transferred like that. We no need to confuse. Okay, data also in our case in this project especially, it is going to play with the packets only. Okay, inside the packet we have data. That's why we are using router here. See how compressed it is and how detailed it is. Okay. In a packet, we have which address we need to go and what is the length of our payload. And we have payloads here and we have parity also. Okay. So that is why we are telling like router. We need a router to avoid errors. Okay. So this will be sent from source to a destination. Okay. Clear or any confusion till now?
Yes, clear.
Clear now or still you have any confusion like how it comes from source like that? Any confusion or clear only? No problem.
Sir, in the like first 1 byte here you write length and channel.
Yeah.
So, like length one in bit that in byte that understood, but channel like what channel it means?
Yeah. Actually, channel in the sense it is address. Okay. Actually, you no need to consider this as channel. Yeah, channel is there, but it is address. Okay. The first 2 bit is of address. If the first 2 bit is 00, then our packet will be transferred from source to 0th destination. Okay. If it is 01, our packet will be transferred from source to first destination. Okay. If it is 10, our packet is transferred from source to second destination. Okay. If that is why we use here channel. It is like a address. It will tell which destination we need to. Okay. Understood no or different doubts?
Yeah, understood. Like one means it will go to destination.
Yeah.
Zero,
Yeah. If it is, we have 2 bits no here. We have 2 bit here no. Like this 0th bit and first bit. These 2 bits are used for that selecting the destinations. Okay.
yes,
If
yes,
it is
understood.
okay. Okay. Is there any other doubts? Yeah, come on. If you have any doubts or if you are unclear in some concepts, you can ask. I will. Okay. As of now, everything is clear or any doubts? We will refer. We will have a brush up tomorrow once again. Okay, no problem. And till now, is there any doubt or any confusion or any concept which you need to know somehow, which you need more detailedly? Anything like that till now?
Yeah, like architecture part, can you explain like it's, one device ones what it like not understood properly?
Yeah.
Like how
Actually,
it
yeah, I didn't like explain till now. I didn't explain this whole detailedly. Okay, I just explained this block. What is the process of this block is for? Like register. Obviously, we know it is for storing purpose. Okay, we are going to anyway. We are going to store some data. The received packet we are going to store, and then we are going to give. At least we need some space, no, to get the data and keep in, and we need to give. We need to deliver to the particular destination. At least we need some storage, for a particular period of time like that. Okay, for that we need register. Okay, and synchronizer is for we have a packet and we need to send that from source to destination. Throughout this process, everything should be in a synchronizer, that is in a timely way. Timely way means it should follow a proper time period. Okay, in this time this should happen. For example, in this time our source should be moved to the packet in the source should be moved to the router. At this time this router will route to the expected destination. Okay, for that purpose we are using synchronization. Okay, synchronizer and FSM. As I told you, see here we have different states. Okay, so if we are in decode address state, then we need to know what is the next state. It will go to the load first data. Okay, after decode address it will move to the load first data state. Okay, so it will identify if we are in a particular state, then what our next state is or what is our previous state. It need to identify, no, our router needs that information. No, for example, if we are in low data state, then what is our next state? That information we should need. Okay, so for that purpose we are using FSM. Okay, and then we have FIFO, first in first out. Why we have 3 FIFO? In the sense we have 3 destinations. For that we are using FIFO. Why FIFO? Whatever the packet inside the packet we have different payloads. No, we have we have number of payloads. Okay, so whatever bit we received first, it should be come out first. Okay, it should not be reordered. Okay, for that purpose we are using FIFO. As of now, I explained these blocks in a overall in a upper level. Okay, we are not going into that right now. We see here in the upcoming session, for each level we have diagrams. Okay, pin diagrams, we will understand. Okay, it is clear now.
Yes. Clear.
Any other doubts, any other doubts or confusion, or any other clarity you need, anything like that? Anything? No doubts, sir.
Sir, the number of destination, if is it 3? That's why we are using 3 FIFO over here in architect.
Yeah, yeah.
Okay, okay.
Okay. Any other doubts?
Like this
Sir,
FIFO can be.
Yeah, please.
Means I am asking like FIFO is in architecture three only used. According to the data packets, it will be less or more, no?
No, it will not be like that. Actually, wait. See, it is different. It is a packet. Okay. In that packet, we have number of data. Okay. See here, this length is there. No, this n. This n will be. This n will. What this n is telling to us? It is telling like how many number of data we have. Okay. But this everything will come under a single packet. Okay. That is what a packet format is of. It have the data which we are going to transfer, which we are going to transmit from source to destination, and it also have the address, and it also have the parity bit. Okay, parity byte. Okay, so this all information are going to transfer, are going to transmit, are going to transmit from a source to destination. So it will not like some packet will be not enough or it will be high. It is not like that. Whatever the packet we give it will decode. That is why there is a stage called address decode in our in our FSM. No, the first stage is address decode. Okay, it will decode and it will send the data. It will load the data here. Okay, in the FSM. Sorry, in the FIFO. Okay, so it will. Okay, how many packets we give? We no need that information. Like I am not telling like we no need. We no need to worry about that. Okay, so if this FIFO is available, it is going to accept. How it is accept? It is going to pass a read enable signal. So after passing the read enable signal, it is going to accept the data. Okay, in and it will give the data out. If it is in some other work or it is busy at that time, if we are giving some input packets, okay, it will not enable that read signal. Okay, so that we can confirm like okay, it is in some other operation, or we can give a busy signal. In that case, we can understand like okay, our FIFO is in busy state, it is in some other work, so we can pass some time after. Like that we can understand. Okay, other than that there will not be like if some packet it can't handle or like that and all, no problem. Okay, that is what now you asked. That is
Means
am I got
I'm
your point?
asking. Yes, means I'm asking here only three people are using, so
Yeah,
it can be more or less possible, no?
more or less in the sense we can add
Means
some
FIFO.
extra people.
Yeah, yes, I'm thinking another FIFOs also I can add, no? Zero
Yeah,
one
if
two.
you can, yeah, actually, yeah, our project is 1x3, but if you need more P4s, that is, if you have more than 3 destinations, yeah, you can add and you can implement signals and you can see what will change based on our knowledge. Our address should be incremented. Okay, if our address is incremented, for example, here we have 2-bit. Instead, if we have 3-bit, what we can address more than we can address up to 8 destinations. Okay, so like that, some small changes we can do and we can implement. Yeah, it is also possible only. That what we should. There are some alterations. That's all, but we can do. It is also possible only. Okay,
I got it.
okay then. Okay, someone any other doubts? Someone I think interrupted, no, or not? I don't know. Yeah, if you have any other doubts, you can ask.
Sir,
See,
FIFO part is
yeah,
not clear. Means why
FIFO,
we are, yeah, like
yeah,
we are using first in, first out. Means then we can use only one FIFO also, na? Means why we are using
yeah.
three?
Actually, we can use one FIFO, but okay, why we are using three in the sense? Okay, we are passing the first data. Okay, first data we passed here, and we have first packet. Okay, if we have a packet which we need to deliver to the FIFO 0. Okay, now we are delivering it to FIFO 0, and let's consider this 3 as, I think we are confusing, like it is same name, no, like FIFO, FIFO 0, FIFO 1, FIFO 2. For that we are considering, we are confusing, but the actual purpose when it comes to reality, let's consider this as three different laptops. Okay, you are using one, I am using one, and your friend using one. Like that we consider. You may search some different data, and I may search some different data, and your friend may search some different data. Okay, in that case, it should route no. So if we use for FIFO, here we are using some general term FIFO. In here it is confusing, but imagine like if we instead of FIFO, if we have some three different devices. Okay, in that case, for different devices, we need to give different data, no? So that is why we have three FIFOs. Okay, we in reality we can consider this as a computer, a mobile, like that we can consider. And if you imagine like that, and if you look this architecture, means it will be good. Okay, so it is like general name, no, FIFO like that. That is why we have some confusion. Like, okay, instead of three FIFO, we can use one FIFO and we can pass, no, like that we are confusing. But the reality is this three FIFO implies three different devices. Okay, that's why I told you, like we are using three different computers, and you may search something, and I may search something, and your friend may search something. So at that time, our router will route the different data to our different computers. Okay, this is what the actual thing is. Okay, understood, no, or still clarity you
Yeah,
need?
yeah, sir, got it, got it.
Yeah. Okay.
Means it means it depends on the number of devices. Yeah, I got it.
Yeah.
Because it is first in, first out. So we the destination we need to send the
Yeah.
data at a time. That's why
Yeah, that is
you.
first in, first out. Why we are using FIFO
Yeah.
here is we will send the data. Obviously, it is going to be in a serial way. Okay, that
Mm.
bits are in a serial manner. So whatever bits we transfer in should be same in the output side also. Okay, that is what whatever the input come first, it should go out first as well. Okay. Either if we reorder means our data may it will come some error. No, we will search something, but the result will come some other thing. No, so for that, to avoid that confusion, we are using FIFO here for data, for proper ordering of data. Okay, if whatever we give in, the same should be come in the output side. Other than that, why we are using three FIFO in the sets? We need to imagine like three different devices. Okay, we may search different. We may expect some different data. So our router need to give the different data to the expected destinations. Okay, clear, no, or still have some confusions like that? Hello, clear, no?
Yes, sir. Clear, clear is it is.
Yeah. Okay. Okay. Any other doubts? Any other?
Oh, no, sir.
No doubts. Okay. Okay. I will share this recording session. You can go through and see if you have any doubt. Not in router, in risk also. If you have any doubt, you can ask. Okay. In the starting, we have some time. No, we are waiting no some time. In that time, if you ask some doubt, means I will solve. Okay. I will clear that doubts. Okay.
Okay,
Okay.
sir.
As
In
yeah, yeah, yeah.
sir,
Continue,
in
please.
yeah, in router we will see the verification using UVM, right?
Yeah. Actually,
Okay.
yeah. We will see.
Sir, we
You are
can do it.
familiar with
Yeah,
you. We
UVM we have completed.
okay. Mm-mm.
We
Then
can do
yeah,
it by
continue.
system Verilog also, right?
Yeah, basically for every design, okay, for every design we can write architecture in a directed way. Directed way in the sense we use our Verila code, no. We use
Hmm.
our Verila code and we just pass our input, and we will check either it is getting the expected output or not. we can use that format, or we can use system Verilog architecture like generator, monitor, driver like that, or else we can use UVM. Okay, sequencer, sequence item. We can use that same architecture. Okay, so whatever for a design, whatever architecture we need, we can implement that. Okay, so for router we have UVM. I think, yeah, we have UVM, but we can implement that using SV also. No problem in that.
Okay.
Okay. Not only for router or like RISC-V like that. For any design, if we need to implement it in a RISC UVM structure, we can go to this UVM architecture. Or if we need SV, system Verilog architecture, we can go to the system Verilog architecture and we can verify using that architecture. Or we need some basic directed testing, means we can do that also. Okay, for every design. As of our project in router, we use UVM. That's all. If you
Okay,
need
sir.
SV, you can use that way. Okay.
Okay, sir,
Yeah.
please share the PPT also.
Yeah, I will share the PPT and share the recordings, and if some materials, if I get some materials, I will share that also. Okay.
Okay. So thank
Okay then. Yeah, okay.
For
Any other
this
doubts?
five like recording,
Yeah.
like will not share. No, please share it.
Uh,
Ask it for but if I not
You can compare. Okay, sure. Okay. I will tell them to share. Okay.
no, yes.
Okay, thank you. Okay.